Every smartphone has a hidden environmental story, one that goes far beyond its sleek design and daily use. As we scroll, tap, and connect, it's easy to overlook the journey our devices have taken to reach our hands. Behind every phone lies a complex web of resources, manufacturing, and global transport, each with its own environmental footprint. openLCA is an open source tool designed to help understand the full life cycle of products from raw materials to recycling. With openLCA, it's possible to trace every stage of a smartphone's journey: energy, materials, water, waste, and more. Discover how openLCA reveals the bigger picture, uncovering the hidden impacts of our everyday technology. Every day, billions of people use smartphones, devices that have become essential to modern life. But what is the true story behind these powerful gadgets? At first glance, smartphones seem harmless because of their small size. Yet, the environmental footprint is much larger than most people realize. Inside every smartphone are more than 60 different elements like gold, cobalt, lithium, and rare earth metals sourced from all over the world through intensive mining. Manufacturing a single smartphone requires significant energy and chemicals, with large factories operating around the clock to meet global demand. Billions of smartphones are shipped worldwide each year, creating a massive transportation footprint that adds to their overall environmental impact. Most smartphones are replaced every 2 to 3 years, leading to a mountain of electronic waste that poses serious environmental challenges. Life Cycle Assessment, or LCA, reveals the hidden costs of smartphones from resource extraction to manufacturing, transport, use, and disposal. LCA also points to better solutions like recycling, modular design, and greener batteries. OpenLCA enables users to uncover the full environmental story behind a smartphone. The software guides you through every stage of phone's life cycle from raw materials to recycling. The first step is to define the goal. Measure the environmental impact of a smartphone across its entire life cycle. The functional unit is set as one smartphone used for 3 years, reflecting a typical usage period. Next, system boundaries are established to determine what is included in the analysis. The process begins with raw material extraction as metals and minerals are mined from the earth to use in smartphones. Manufacturing and assembly follow, where components are produced and assembled in advanced factories. Distribution is the next stage, tracking the smartphone's journey across the globe to reach users. The usage phase covers daily charging and operation of the phone throughout its lifespan. Finally, end of life considers what happens when the phone is recycled or disposed of. With all stages mapped out, openLCA allows users to build a life cycle model connecting each step within the software. For raw materials, data is entered on mining lithium, cobalt, gold, and plastics, revealing impacts such as deforestation and emissions. OpenLCA visualizes these impacts, including deforestation, toxic byproducts, and high carbon emissions. The software displays Sankey diagrams to show how materials flow through the phone's life cycle. For manufacturing, users add data for electricity, heat, and chemical, watching the model expand. Chip fabrication, battery production, and screen assembly are identified as major contributors to the phone's environmental footprint. Results show that manufacturing is responsible for the largest share of carbon emissions, often more than half of the total. OpenLCA provides energy demand charts and a breakdown of emissions for each stage. For distribution, global transport is modeled, showing the movement of phones by ship, plane, and truck. The carbon footprint of logistics is calculated and displayed within the software. OpenLCA enables comparison of different transport routes and their environmental impacts. During the usage phase, data is entered for electricity used to charge the phone each year. The impact varies depending on the local electricity grid. Coal heavy grids result in higher carbon emissions. OpenLC allows users to explore scenarios: renewable energy versus fossil fuels. At end of life, the software considers landfill, incineration, and recycling options for smartphones. Recycling recovers valuable metals such as copper, gold, cobalt, reducing the need for new mining. OpenLCA highlights avoided impacts by crediting materials recovered through recycling. The next step is to select an impact assessment method within OpenLCA. The software offers methods such as CML, which covers climate change, acidification, and eutrophication. Recipe is another method addressing human health, ecosystems, and resource use. IPCC focuses on the carbon footprint and global warming potential of the phone. For mobile phones, recipes often chosen to capture a broad range of environmental impacts. The final step is to analyze the results. Findings show that the manufacturing is the largest contributor, followed by usage, transport, and end of life. Manufacturing alone accounts for 50 to 70% of the total carbon footprint. The usage phase makes up 20 to 30%, depending on charging habits and the electricity grid. Transport adds another 5 to 10% to the total impact. End of life is about 5%, but recycling can significantly offset raw material impacts. OpenLCA produces bar charts to show the impact of each stage in the life cycle. Pie charts reveal the distribution of carbon emissions across the stages. Contribution analysis pinpoints which component, battery, screen, or chip, has the greatest environmental impact. Life cycle assessment of mobile phones reveals surprising truths. The data highlights the most significant environmental impacts across the phone's entire life cycle. The battery is the most environmentally costly component, responsible for a large share of the phone's total impact. Extending a phone's use by just 1 year can reduce its total environmental impact by 30% or more. Small choices make a big difference. Recycling 1 million phones can recover large amounts of valuable materials, reducing the need for mining and resource extraction. About 16,000 kilograms of copper can be recovered from recycling a million phones. Recycling also yields around 350 kilograms of silver from 1 million phones. Even 34 kilograms of gold can be recovered, showing the hidden value in discarded phones. Rare metals like 15 kilograms of palladium are also saved through recycling, highlighting the importance of proper e-waste management. Modular and repairable phone designs such as Fairphone achieve much lower environmental impacts in LCA studies. Sustainable design is key to reducing the footprint of electronics. The largest environmental footprint of a phone is created during manufacturing, not during its use. Choosing sustainable products and recycling can make a significant difference for the future. Up next, see a real life demonstration of OpenLCA.
We will see a navigation panel on the left. This is where all your data is organized. It has folders like databases where all the projects are stored, flows, which represents inputs and outputs like materials, energy, and emission, processes, which describes how flows are converted into products, product systems, which connect processes into a complete model, and lastly, impact assessment methods, which calculate the environmental impact of the material chosen. First, we begin with setting up a database. OpenLCA works with databases that contain information about materials, energy, and environmental emissions. Without these, we cannot model. These databases can be downloaded from nexus.openlca.org. For performing the LCA of a mobile phone, we have chosen two databases, LCI and LCIA. For LCI, we have chosen OZ LCI 2019, and for LCIA methods, we have used EcoInvent version 3. An LCI database is a collection of background data about processes, materials, energy use, emission, and waste. An LCIA database contains methods to interpret LCI results. It does not give you raw inventory data, but instead provides characterization factors to translate emissions and resource use into environmental impacts. Now that the database is ready, we can begin modeling. Every LCA begins with defining the goal and the scope. The goal is to study the environmental impact of a smartphone for a functional unit of 2 years. This ensures that we are analyzing the product from cradle to grave. Now we'll understand how an LCA is performed in OpenLCA. In OpenLCA, a flow represents something that enters or leaves a process. Each flow has a reference flow property, which is its unit, for example kg, kilowatt per hour, or piece. Go to the flows folder, right click on it, and click on new flow to add all the flows that you want in the LCA. Now talking about the processes, a process is a building block that describes how inputs are transformed into outputs. In LCA, we have added all processes from cradle to grave. We can see that there are all the processes, for example, battery production, display production, phone assembly, transport, use phase, and end of life phase. To create a new process, we have to click on the processes folder, right click on it, and click on the new process. Then we can add all the processes that we need to maintain the LCA for the product. Now, when we click on a process, for example, phone assembly, we can see all the inputs and outputs of each process. Input flows are materials and energy that go into a process. For example, electricity, aluminium, plastic. For example, for a phone to be made, we need battery, aluminium production, display assembly, and electricity. And output is the output or product or emission that come out of a process. For example, after the phone assembly, we get a smartphone. Now talking about product systems, we can see that here I have added phone assembly as a product system. Product system connects multiple processes into a complete model. We can right click on product systems and click on new product system to add a product system. Now, to interpret results, we need an impact assessment method. Now here we have chosen eco invent LCA methods, and among that we have chosen recipe midpoint H, which calculates impacts like climate change and toxicity. Now after all this, we need to calculate the results. For that, we need to double click on phone assembly, and we can see here that there is a calculate button. Now click on that calculate and select LCIA method. Here I have chosen recipe midpoint H for calculation of LCA. Now click on finish, and then we can see the results of the open LCA. Now openLCA will run the calculations and show the results. Now we can analyze the results. The results show that climate change impact is about 2.5 kg CO2 equivalent per phone. This is mainly due to the energy intensive processes like battery and component production. But what's interesting is that climate change is not the only hotspot. We also see very high impacts in human toxicity and ecotoxicity categories. For example, human toxicity is over 4300 kg, 14 dCB equivalent, and marine ecotoxicity is around 2.5 kg. This means that emissions from metals, chemicals, and electronic manufacturing pose significant risks to both human health and ecosystems. So, the key takeaway is that battery production and materials are the big contributors to impact. Toxicity impacts are as critical as carbon dioxide emissions in electronics. Recycling and cleaner energy sources can greatly reduce the overall footprint.
LCA of laptop. Similarly, we have performed the life cycle assessment of the laptop, and these are the outputs of this assessment. Thank you.